This is the third part of the fourth chapter on agonist efficiency. And in this chapter, we have been concerned with the nature of the gating isomerization itself. In the first part of this chapter, we defined the parameter phi, showed its distribution, and showed how we measured it. And in the second chapter, we gave an interpretation to phi values and that distribution, namely that there are 5 intermediate transitions that join A2C and A2O, and these 5 transitions separate 4 intermediate states. These are large asterisks because we predict there should be a structure where the agonist and extracellular domain have changed from C to O, and in another structure in which the first 3 groups, the purple, blue, and green groups of amino acids, will have switched to their open conformation. So we have named these 5 transitions that separate the intermediate states: hold at the binding site, twist of the extracellular domain, tilt of the transmembrane domain, rip at the gate, and pop having to do with water. Now we're going to try to use this model, which gives the number, sequence, landscape, and map of conformational change, and put it together with what we think we have learned about agonist efficiency, namely that catch and hold are linked by a zipper mechanism, linear free energy rate relationship in a zipper mechanism, and we're going to extend that mechanism into the rest of the isomerization. So that zipper mechanism is that linear free energy relationship is shown by this symbol, this paperclip symbol, showing that catch here in orange and hold are linked by a linear free energy relationship where catch promotes hold by lowering the transition state. And that is what I call the zipper mechanism. And we have shown, or we have proposed, that hold, twist, tilt, rip, and pop are sequential subevents inside of the rest of the gating isomerization, with the transition state being located somewhere in the tilt rearrangement, and that these asterisks represent the intermediate states that someday we hope we will find structures for. Right now we have C and we have AO, but we don't even have AC, which is this state right here, which is the closed ligand state. It can be considered an intermediate state in this process. And just to remind you, so what we're going to do is we're going to link all these by the paperclip, by the same linear free energy process that we use for catch and hold. So catch promotes hold, promotes twist, promotes tilt, promotes rip, promotes pop. They're all going to be linked in a big, long linear free energy relationship to connect C, unliganded C, with liganded O, the activation of the receptor. And just to remind you that the blue line here highlights the states that all have high affinity. Everything after hold is a high affinity state. So I've given these names now with primes, AC prime, AC double prime, triple prime, and quadruple prime, that I think together these 4 states represent flip, are also called flip. But this is the AC state, which everyone puts in there, even though it hasn't been found structurally. That's the low affinity state. And of course, there's a very low affinity state here before the agonist has formed a low affinity complex. And the black line represents all the states that are non-conducting or shut, all the way from C. In this model, the only states that is conducting is O. And this shows the linear free energy relationship between those states. So this is the model that we have shown up above, where catch and hold and everybody else is linked by a linear free energy relationship. And I want to say that this is not just wild speculation or just derived by analogy to catch and hold, that the linkage, the linear free energy linkage throughout the isomerization, I think that this can be used to explain an unexpected experimental result shown, I think, in Chapter 3, which is shown here below, which is that the association rate constant of agonist to O is not only faster than to C, but is roughly at the diffusion limit and the same for many agonists. So here, ACH, carbachol, and TMA all have approximately the same association rate constant, which is near the diffusion limit, which is this dashed line here, 4 times 10 to the ninth. Choline is slower. But these three agonists are roughly at the diffusion limit, and they are all significantly faster than to C. Notice that this is a log scale here. So this is 10 to the 10th, and choline is 10 to the 6th. So the question is, why are these agonists that all have different, very different affinities, both low and high affinities, all have the same on rate constant when the channel is O, but very different on rate constants when they're to C. You recall that we use this reduction in C with a reduction in EC50 to divide binding into diffusion and catch. So now we want to try to use this model shown above to try to explain why these guys are at the diffusion limit. And the idea is shown in this thermodynamic cycle to the right, which is this line at the bottom is the catch conformational change, and this line, this purple line here, is the hold conformational change. And we have, in Chapter 3, we showed that the catch event lowers the transition state for the hold event so that hold can take place. So that hold very rarely takes place without catch happening. That's given by this dashed line. So the difference between the thickness of the lines here, the thickness of the lines represents the equilibrium constant for the process. So the fact that you have a very thin line with it before catch and a reasonably thick line after catch means that catch promotes hold. That's what this arrow means. Now in a thermodynamic cycle, there is something called microscopic reversibility, which means that the getting to an endpoint is the same regardless, the energy is the same regardless of the path. So if this path is very small, then this path must be very large to close the cycle. So that catch, so that means if you find yourself having undergone hold, rarely it will happen. If it happens first, you're very rapidly going to also catch. So the microscopic reversibility means that if catch promotes hold, then hold promotes catch. And this must happen also throughout the rest of the isomerization. So hold and twist, twist and tilt, tilt and rip, rip and pop, all promote each other. So what this means is that if I make a mutation that makes the channel open constitutively, which is how we made these measurements here on the left, we added a mutation, the channel was open constitutively, and we added a little bit more agonist, and we were able to detect the actual binding event to the open state and get the rate constants into and out of the open binding site. If you make a mutation that does that, and here I'm using the mutation V218Y, that was the extreme mutation of that M1 pi helix residue after the pi helix, or inside the pi helix. And if we make a mutation here that makes that happen with great probability and therefore increases open probability, what that mutation is going to do is going to not only promote the subsequent events in the chain, it's going to promote the preceding events in the chain. So you're going to get up and down. It's going to be bidirectional is what's going to happen. You're going to get all the way through to catch, because catch promotes hold. So in this case, tilt promotes twist, promotes hold, promotes catch. So that's why when you make these mutations that cause constitutive activity, you are also promoting catch all the way across. So you cross, this is where everything to the right here is called, to the right of this point is called gating, and everything to the left is called binding. But the linear free energy actually links those two. So you cross the binding gating divide and enforce catch when you make mutation that causes constitutive activity. So microscopic reversibility ensures that catch accompanies catch is accompanied by catch accompanies constitutive activity. So finally, let's put this together and show you how I imagine the energy landscape for gating changes when you add an agonist. The inset here shows what you recorded in our patch clamp. The patch clamp is great as long as you're not interested in things that are faster than a microsecond. And as we're interested in 100 nanoseconds events, so these things sort of blur together into these energy barriers that we draw. But in fact, they're corrugated with lots of bumps inside. And that's what I've expanded out here, just tried to show what the bumps are. Now, this is not done quantitatively according to Phi, but this is just the idea. And the idea I'm going to put together is that the gating isomerization acts as a zipper. And I'll show this twice. First, let's focus in on the energy landscapes. The agonist arrives. It lowers the energy. Sequentially lowers the transition state of the next event, allowing it to occur. And this blue energy landscape turns into this black energy landscape, and that's shown here in these inserts at low bandwidth resolution. So you go through. After diffusion, you have catch, hold, twist, tilt, rip, and pop. And now I want to show this again in structure. Let's focus in on the structural part because we do have Phi gives you the location. Our Phi map allows us to locate these in the protein. So that's the ion shown up above, and you can see the binding site with the ligand inside. And now we're going to go through catch, hold, twist, tilt, and pop. And then the ions can go through. So that's my imagination on the energy landscape changes in ACH receptor gating, and it's done through a zipper mechanism wherein each preceding conformational change in the sequence promotes the subsequent conformational change by lowering its transition state. So the idea being that the structure of the intermediate, which has one domain has become active, must match the transition state for the subsequent conformational change. So that's the end of the pamphlet on agonist efficiency. We did a definition. We defined efficiency. We described some patterns. We proposed a linear free energy relationship between catch and hold, between binding and gating. And we extended this linear free energy relationship throughout the gating isomerization. And I think this might be a good way to move energy across distance only by local conformational change. So each of these Phi blocks is within our 18 angstrom distance for energy transfer inside the protein. So you move 1, 2, 3, 4, 5 of these things in a row, and that's the way you move energy over distance, only using local conformational changes. So I hope you will stay tuned for the acknowledgement sections which follows.